Today I'm going to talk about a very simple but powerful idea and a kind of like recent development within a Lightning Network as far as how we're developing it as a protocol. It'll easily be conceptually the most boring talk here today, but I'm hopefully by the end of the day convince you that, that this is a pretty big advancement for how we are going to move forward with the Lightning Network and just sort of future protocol developments. And so the topic of the day is serialization and how we encode messages between nodes in the Lightning Network and how we exchange data. If you look at the BOLT specifications, BOLT stands for Basics of Lightning Technology. It's an RFC sort of specification that defines how the message types look. And most of what's in there is how are those encoded and when are they sent between peers and how do you do that properly without sort of breaking expectations of other nodes. This work sort of comes out of about a couple years of interacting with other implementations and seeing sort of where the shortcomings of, specifically when they come to message serialization and how we can improve that in order to sort of bolster how we're able to advance with the Lightning Network as it is today. So we'll dive in. If you look at traditional message serialization, let's say we wanted to send a message that has information about a user. You might have the name, address, and phone number. And typically, you just kind of like write those fields onto the wire sort of in order. This is how messages work in sort of the Bitcoin protocol and stuff like that, and how they work in Lightning today. Now let's say you want to add a new feature. Let's say you want to add a credit card number. The obvious place to put that is right after everything else. So, and that's really easy when everyone agrees that, okay, we're going to add the credit card number next, and everyone actually implements that and is able to read that data. If you're on an older node and you just add data to the end, most nodes will basically just stop reading after they get to the phone number. So what that allows is that they'll basically just ignore the extra data, which is good. I mean, if that means it doesn't break backwards compatibility with old nodes when you add new fields. This becomes a little more complicated, for example, when you have multiple features that you're trying to implement. Let's say the credit card number is being used because you need to hook up some Venmo-like thing, but at the same time you're trying to add another field, which maybe is like their Facebook ID or something. And then you have to have this sort of question. If I don't want to implement the Facebook feature for obvious privacy reasons, do I have to actually know how to read that message or read that Facebook ID in order to skip it? And this becomes a problem when you have these multiple different features being added at the same time, because people may want to implement them at different times and stuff like that. So the main reason that this becomes an issue is because of the coordination involved in sort of agreeing where to put these fields, and also implementations may want to have different agendas in terms of what they prioritize, and so they may want to build them out, even though at some point they may all implement them. And lastly, this enables a sort of it makes experimentation difficult because everyone has to agree. And if we all have to agree up front to every single little change that happens, then it reduces the amount that we can sort of experiment and try out new things. And that's really hard to do today currently. So that's sort of what we're trying to address here. Now this problem has been sort of addressed in a number of ways over the years. If you guys are familiar with Google protobufs, that's sort of a solution to this. Google uses this sort of library for handling all message serialization internally. It allows all their internal orgs to add fields and change things in ways that are forward and backwards compatible. And for reasons I'll get to later, we could not use that here, so we had to sort of develop our own. So this is kind of like a lit buff, if you will. So the basic primitive that we use here is, instead of writing the fields as they appear, just a name, a phone number, a credit card number, whatever, we are going to encode them in this sort of thing that we call the TLV record. TLV stands for type length value. That's sort of just a generic name that we call this sort of serialization. Within the Lightning Network, you'll see in all of our logs that we just reference TLV all the time and kind of use it as this magic bullet kind of thing. So, but the basic idea here is every time you add a new field, it has this sort of identifier, a type, and here we have 42. So the other thing it includes is its length. Every field also says how big it is. And finally, then the value, which is length bytes of whatever the content of that sort of field you're trying to send. Now, the cool thing about this is I don't have to know what that is actually in the value in order to be able to skip it. So this addresses that first problem on the first slide, where if someone else wants to add a new field, but I just need the credit card which comes after it. I didn't know how to skip it because I don't even know what it is. Here, because everything is sort of self-describing, I'm able to essentially skip fields that I do not understand. So to visualize this, let's say I'm parsing this sort of like serialized stream, and I recognize this type. I recognize this first type, so I'll go ahead and like inspect the length, and then pull out maybe it's the name, address, whatever. Now, when I get to something that I don't understand, I simply read the length and just skip the next n bytes. And that's how we sort of like maintain backwards compatibility. We're able to add new fields. People are experimenting. They can add data without actually being able to break sort of the serialization on other nodes, and they're able to still communicate, even though they may not be speaking exactly the same features. And then finally, you're able to parse fields that succeed that. So this is sort of the basic premise, and this is how, in general, like protobuf works, and this is how what we are going to be implementing in Lightning is going to work as well. And this is a pretty radical departure from what we have been doing, and pretty much everything that we know in Lightning will come to use this as sort of like a base layer just to maintain interoperability and expand on our ability to like experiment and like drive further development forward. Let's see. So now, getting to the reason why we couldn't use protobuf, one of the challenges that we have to do, one of the challenges that we had is sort of how to develop a canonical encoding. And a canonical encoding is, in a sense, a deterministic encoding. So when you have a message and different people encode it, it always needs to come out to the same thing. And this needs to be true even if I don't understand what the types are. So the main reason you need this is because some of the messages in Lightning are signed. They have a cryptographic signature over it. This is what we use for sort of gossip traffic. And if those encodings are not deterministic, then our signatures may not validate when they're sent over the network. So we need to have a deterministic encoding so that we can actually propagate gossip messages and do stuff like that. So by having this, that enables us to actually extend even the gossip messages with new fields in a backwards and forwards compatible way. Now, the other one is that you also need to be able to verify that it is canonical and that it's like properly encoded without knowing the types either. So that means that the encoding has to be independent of the actual things you are encoding, which is kind of weird. But and finally, it needs to be efficiently verifiable. So we kind of like accomplish all of these things using a very simple way of doing this, and that is just you write the types in sorted order. So if I don't know the types, I'm still able to look at those and verify that they are always increasing. The next one I read is bigger than the last one. And that allows us to very efficiently accept messages and check that they are properly formed without incurring too much overhead. So this is important when you're processing thousands of gossip messages per second. And so this was one of the things that took a lot of time to nail down. And this is the issue with protobuf and why we couldn't use it. Actually, if you look at a very early Lightning prototypes, the network itself used protobuf as the main message serialization format. And we quickly realized that this was going to be an issue when it came to these signatures because different versions of protobuf allow these reorderings and they're not deterministic. So this was, this has been the work of many people within the Lightning community. Rusty, Lisa, Christian Decker, Rose Beef. A lot of us has kind of collaborated and gotten feedback on the sort of approach. And we're very excited to kind of start shipping it because most of the things that are coming up will end up using this in some way, shape, or form. So some of those are, the main two places we're going to use this is the wire messages. So all the messages between where you send back and forth, or the messages you send back and forth between nodes in the Lightning Network, we'll use this format. There's a current proposal to basically do extended gossip queries, which allow more fine-grained control of requesting different views of the graph from other nodes. And this is one active proposal that actively uses this. Another place we're going to use this is an onion payload. So when you actually do the onion encryption and send these onion encrypted packets through the network, at each hop, there's going to be data that each one of them gets. Mostly it's, how much do I need to forward, where am I sending it to, and time lock values. So those are all going to be encoded using this, and what that allows is future developments where we want to modify what data we're actually sending to those nodes without breaking backwards compatibility with all the other ones. And especially, this is really, really powerful for the data you encode to the final destination. This enables things like spontaneous payments, where basically a spontaneous payment is where I don't have to generate an invoice to receive payments. So instead of generating an invoice where sort of the receiver generates a pre-image, the sender actually generates the pre-image and then just puts it in the final like onion packet or puts it in the final payload for the final recipient. And then when they get this, they just send back the pre-image and get the payment. And it's kind of like it takes no interaction for me to just like send to your node. All I need is your node's pub key. So that'll be a really cool improvement from a UX perspective. That you don't need to have this sort of like invoice round trip in order to be able to pay people. And that is all enabled by this because there's this optional field, and if I see that, I can grab the pre-image and take the payment. There's atomic multipath payments, which is another development that mostly works in the same sort of sense as that spontaneous payment example. You basically just embed this extra data to the final hop. And there's a lot of other really cool things you can do when you have this like really big flexibility of adding new fields. There'll probably be a lot of application layer things that end up taking advantage of this. You can stick application specific data where you just like send memos or other things, messages, who knows. But it's very flexible. So like you can do this in a way that doesn't break all the compatibility that we expect and like sort of the reliability, because if everyone agrees to this sort of basic format, then we're able to like move forward and people experiment with new features in terms of what they send. And yeah, basically all the things in the Bullet 1.1 spec are mostly predicated on getting this like agreed upon and merged. So I think we're in the final steps of actually doing that. So we, after that, we can kind of expect like a pretty big ramp up in terms of the new features that are being deployed. And finally, all of our favorite reason. No. The last bullet doesn't work, but it says orange number up. Anyways, thank you very much. Thank you.